Hello all. In this examples video, we will look at an example in single slit diffraction. Our first question asks us to explain, by reference to waves, the diffraction of light at a single slit. I'll pause now so that if you would like to, you can attempt this question. All right. So if we take a look at our solution, the first thing we will want to make sure we pay attention to in this question is by reference to waves. So we're going to need to discuss waves. And it's simply asking us to explain that diffraction happens, that there is diffraction. Okay? So the solution says the wavefront within the slit behaves as a series of point sources, which spread circular wavefronts from them. This is a restatement of Huygens' principle and should definitely be in your full answer. It then goes on to say that these secondary waves superpose or are superimposed in front of the slit, and the superposition of these waves produces the diffraction pattern. If you use the word interference, that would work as well. So you could also go on to explain that different parts of the wavefront, namely the top half of the wavefront and the bottom half of the wavefront, would interfere with each other to produce the interference pattern shown. Our second question asks, light from a helium neon laser passes through a narrow slit and is incident on a screen 3.5 meters from the slit. The graph below shows the variation with distance x along the screen of intensity I of the light on the screen. The wavelength of the light emitted by the laser is 630 nanometers. Determine the width of the slit. All right, so you're given a graph here, and you're asked to determine the width of the slit. In order to do that, I'm going to give you a pause. If you need some time to try the problem, and pause the video. So what you're going to use is our fundamental relationship, theta equals lambda over b. But you'll notice that this particular graph, you're not given theta directly. So x is the distance along the screen. That means you need to go and find theta. So to find our appropriate theta, we're going to take our distance along the screen to that primary minimum right here. And we're going to say that that is about equal to 3 millimeters. And so to get our angle, we're going to use the small angle approximation that says that theta is about equal to sine theta for a particular triangle. And therefore, sine theta is about equal to s, the distance along the screen, divided by d. This should be familiar to you from the double slit formula. And so we do, therefore, s over d equals 3.0 times 10 to the negative 3 meters divided by 3.5 meters, and that gives us our angle 0.86 times 10 to the negative 3 radians. Okay, 0.86 times 10 to the negative 3 radians. With that value, we can then get the wavelength of light by saying that theta is equal to lambda over b, and therefore if 0.86 times 10 to the negative 3 radians is our theta, then lambda is 630 times 10 to the negative 9 nanometers, and that gives us a value for the slit width of 0.73 times 10 to the negative 3 meters. Our final question asks us to state two changes to the intensity distribution of the central maximum when the single slit is replaced by one of greater width. To answer this question, you want to consider two changes. So the first, almost certainly foremost on your mind, is that if the single slit is replaced by one of greater width, then using theta equals lambda over b, we can say that with greater b, okay, with greater slit width, we will find that theta gets bigger. And so we would, theta gets smaller. So we would expect the width of this central maximum right here so that width right there should decrease. The other thing that will happen though is that more light is going through the slit. There's an increased intensity of light going through the slit. If you were to divide that slit in half, there is more light both on the top half and on the bottom half. And as a result, you would also expect the central maximum to increase, that intensity will increase. And those are the two changes being asked for here.